Hello everyone, welcome back to Grade Up. My name is Deepti Mittal. So guys, in this video lecture, we are studying about computer organization, and the subtopic in computer organization which we are studying is instruction pipelining. Till now we have discussed basics and performance analysis of pipelining, then a successful pipelining which is risk pipelining, then the next concept which we studied was dependencies in the pipeline, or the problems which is caused by the pipeline system, which are faced by the pipeline system. Now we are going to discuss some previous year questions on this topic, pipelining. So guys, till now I have not discussed any question on instruction pipelining. Now I am going to discuss some of the questions on instruction pipelining from previous year GATE. So let us start with that. This question, see, this question was asked in GATE CS 2018. So before starting with the question, I would suggest take a paper and pen and solve questions along with me. And somewhere if you need to access the calculator, just use GATE virtual calculator to get fluent with the interface of that calculator. Okay, let us start with this thing. This question was asked in GATE CS 2018, that is the most recent year, this year, and it was asked for 2 marks. Let us see what this question is asking. The instruction pipeline of a RISC processor has the following stages. These are the stages in the RISC processor: instruction fetch, instruction decode, operand fetch, perform operation, and write back. See, the pipeline, RISC pipeline which we have studied, there it is something like execute and memory access. But stage doesn't matter. Here functionality we can understand by their name, that is here operand fetching is done and here some ALU operations are going to be performed. So don't you worry about that. Now let us see what the next thing which is given to us. The IF, ID, OF and WB stages take 1 clock cycle for each and every instruction. That is, these stages will take only 1 clock cycle for processing the instruction. Guys, I have told you that we might have a non-uniform stage pipeline delay. That is, we can have a pipeline where delay of each and every stage is not uniform. So this is the case of such pipeline. Here ID, OF, WB is having 1 clock cycle delay, but see, in the PO stage, for some instructions are going to take 3 clock cycles, some 2 and some 1. This PO stage is having different delays for different instruction. Okay, that is 40 instruction. It is given that you are having a sequence of 100 instructions, and in the PO stage 40 instructions are going to take 3 clock cycle, 35 instructions are going to take 2 clock cycle, and remaining 25 is going to take only 1 clock cycle. Assume there are no data hazards and no control hazard. It is already saying that we are not having any data hazard, no data dependencies and no control dependencies. So what this line means? What does this line mean? Tell me what this line means. This line means that is we are not going to have any stalls while executing the instruction due to data hazards and control hazards. Now let us see what this question is asking to us. The number of clock cycles required for completion of execution of the sequence of instruction is. It is asking us the number of clock cycles which is required to execute this particular instruction. See guys, we are having 5 stages: IF, ID, OF, PO and WB. All are going to take only 1 clock cycle, and it is having different configuration. For 40 it is going to take 3 clock cycle, for 35 instruction it is going to take 2 clock cycle, and for remaining 25 instruction it is going to take 1 clock cycle. The strategy which we have studied till now is every stage was going to take only 1 cycle. Then we studied the formula something like k plus n minus 1 for n number of instructions and k number of stages in the pipeline. But now we have to observe what is the strategy which we are going to follow. So let us see. See, these 40 instructions are going to take 3 clock cycles in while executing. You are having sequence of 100 instructions. 40 is going to take 3 clock cycle in PO. 35 is going to take 2 and 25 is going to take only 1 clock cycle. So let us start with the execution of first instruction. First instruction is going to pass from all these 5 stages. You know, first instruction take k clock cycles. Here stages are 5, but this PO is going to take 3 clock cycle for first instruction in these 40 instruction. Then for first instruction we will have clock cycle delay of, this is for IF, this is for ID, for OF, this is for PO, and this is for WB, that is 7 clock cycles for first instruction. And for the next upcoming instructions, what we have studied was what we are going to add. We were going to add only 1 clock cycles, but here PO is going to take 3 clock cycles. So this is the reason we are going to add 3 clock cycle for one instruction, because that will be the maximum delay which is going to be carried out. Okay. Then for the remaining 39 instruction, this is for first instruction. For the remaining 39 instruction in this 40 instructions, in these 40 instructions, it is going to take 39 into 3 cycles. Because these stages can be overlapped now, but this cannot be overlapped. This is going to take 3 cycles. Now we have completed the execution of these 40 instructions. Then we have to execute these 35 instructions. Same is the procedure we are going to take with these 35 instructions, because these 35 instructions also going to be overlapped for these stages, but it is taking POS 2. Number of cycles is equals to 2 in PO stage. So for these 35 instructions, number of cycle needed is 35 into 2. Okay. And for these 25 instructions, we are going to take only 1 clock cycle, because PO, perform operation stage, is taking only 1 clock cycle over here. So these 25 instructions is going to take only 1 clock cycle. So tell me what is this? 9 3 are 27 to 117, 70, 25. So total number of clock cycles which is going to take is 7 plus 117 plus 70 plus 25. Then it is 124 and 95, which is 219. Therefore, this execution sequence is going to take 219 cycles. Okay, I think you are clear with the concept why we have taken these 3 cycles, because this PO is going to take 3 clock cycles and all these 1 stages are overlapped. So this was the question which was asked in your GATE CS 2018. It was a good question. Okay, let us move towards next question. See, this question was asked in GATE CS 2016. Again, it was asked for 2 marks. Guys, from pipelining, questions are asked very frequently. So be fluent with the concepts of pipelining. Let us see what is the question. Consider a 3 GHz processor with a 3-stage pipeline. What this 3 GHz means, that is we are applying a clock of frequency 3 GHz for the pipelining functioning. Okay, for the functioning of that pipeline, we are applying a clock of 3 GHz. With a 3-stage pipeline, our pipeline is going to have now 3 stages, and the stage latencies are T1, T2 and T3. We are provided with the delays or the time every stage is going to take for processing, which is T1, T2 and T3. And here we are provided with a relation between T1, T2 and T3. It is 3T2 by 4 is equals to 2T3. It is the relationship between delays, stage delays. Okay. Now it is saying that if the longest pipeline stage is split into 2 pipeline stages of equal latency, that is if we are going to find, see, we are provided with 3 pipeline stages. Delays are T1, T2, T3. What we are going to do? We will find the stage with maximum delay and we are going to split it in such a way it will be split into 2 stages of equal latency. Suppose it was having 4 nanosecond of delay previously. Now the new strategy is to divide it into 2 stages, T21 and T22. Now your pipeline is going to have 4 stages, but the delay over here is 2 nanosecond and 2 nanosecond. Now it is asking me the new frequency. What will be the new frequency of my circuit or the new pipeline which we have developed? So the procedure is, first of all I have to find out the stage with the maximum delay, then split it and then find the frequency. So let us see how we are going to do this question. We are provided with the relation between these three stages. Okay, suppose let us solve it. 4t1 will be equal to 3t2 is equals to C. This is t1 is equals to 3t2 by 4. So it will be 4t1 is equals to 3t2. And this is 3t2 by 4 is equals to 2t3. Then it can be written as 3t2 is equals to 8t3. Then how we can write this? 4t1 is equals to 3t2 is equals to 8t3. So see, we are having 4t1 is equals to 3t2 is equals to 8t3. Or if I want to find out the ratio C, t1 upon t2 can be written as 3:4 and t2 upon t3 can be written as 8:3. And the common ratio t1 is to 2, t2 is to t3 can be written as, these two should be equal. So it can be written as 6:8, 6:8, 8:3 can be written as 6:8:3. So this is the ratio of their latencies. Now let x be the some constant. So t1 can be written as delay of 6s, t2 can be written as 8x and t3 can be written as 3x. And this is the basic mathematics. Now you tell me which of the following stages is having the maximum delay over here. T2, because T2 is 8x. So I am going to divide this into two equal delayed stages. See the same thing, if the longest pipeline stage, that is the stage with longest pipeline delay, is split it into two pipeline stages of equal delay. So according to my new design, I am going to split it into two parts and then I will find the new frequency. First of all, see, the longest delay over here is 8x. And I have already mentioned, when you are having pipeline where stages are having non-uniform delay, then clock cycle TP is equals to the stage with the maximum delay, that is 8x. Then, and your TP is always equals to 1 upon your frequency. Here what is your frequency? 3 gigahertz. So see how you are going to calculate. 1 upon 3 gigahertz is equals to 8x, or what can I say, 1 upon x is equals to 24 gigahertz. Okay, we are having the value of 1 upon x now. Now according to the new design, just remember this thing, I will write here, t1 is equals to 6x, t2 is equals to 8x and t3 is equals to 3x and 1 upon x is equals to 24 gigahertz. Now I have divided into two pipeline stages, 4x, and 4x will be the delay because it has to be split into pipeline stages with equal delay. So now 6x, 4x, 4x and 3x. Now I have to find out the new frequency. Before that, tell me the time period which will be taken here will be, the time period which we are going to take is the maximum stage delay, and the maximum stage delay over here is 6x. So it will be 6x and your frequency will be 1 upon 6x, and you know the value of 1 upon x. 1 upon x is 24 gigahertz and your 6, it is going to be 4 gigahertz. This is the way you are going to find out the new frequency for your pipeline. So the answer over here is 4. What was the procedure? First of all, you have to find out the pipeline stage with maximum delay. Then find out the value of 1 upon x and then divide it into the equal delayed stages and then again find the frequency. So this question was also a very good question. If you are not good with the concept, you cannot solve this question. And it was asked in GATE CS 2018, the recent years. So we can say that this pipeline concept is frequently asked. Let us move towards next concept. See, this question was again asked in GATE CS 2016. Again it was asked for 2 marks. Let us see what is the question. The stage delays in a 4-stage pipeline are, we are provided with the delays of each stages. We are having 4 stages, mark it as S1, S2, S3 and S4. Delay over here is 800, 500, 400 and 300 picoseconds. Okay. The first stage with delay 800 picoseconds is replaced with a functionally equivalent design involving 2 stages with respective delays of 600 and 350. Initially, we were having this S1 with delay of 800 picosecond. Now, we are replacing it with 2 stages having delays 600 picoseconds and 350 picoseconds. Now, it is asking me the throughput increase of the pipeline is in percentage. Now, it is asking me the throughput increase, or what we can say efficiency increase, or the improvement or the speed up which is achieved by using this pipeline system. Okay. Previously, we were having 4 stages, and if you have to find out the cycle time TP for your previous pipeline or the old system, you are going to take TP as 800 picoseconds. And you know, for execution of instructions, you are going to, for execution of instructions in a pipeline, your execution time is 1 cycle. Your cycle time should be, cycle per instruction should be 1, and cycle time here is 800 picoseconds. So your old execution time was 800 picosecond. Now your new system is having 5 stages, 600, 350, 500, 400 and 300. Now your ET of new system is always k plus n minus 1 for executing n instructions. But here we are generalizing the case. We are going to execute only 1 instruction. For this 1 instruction, your execution time is 1 cycle. And tell me what is the time period of this cycle for the new pipeline which is obtained. It is going to take the stage with maximum delay, which is 600 picoseconds over here. So the delay will be 600 picoseconds. Okay. Now find out the speed up. Speed up formula is ET of old system upon ET of new system. What was the ET of old system? It is 800 and it is 600. When you are going to divide these two, you will get 4.3, which is 1.33 and so on. Okay. So now see, this is 1.33. Initially, you were having a system with 800 picosecond of delay. Now, you have developed a system where execution of 1 instruction is going to take 600 picosecond. Definitely, you have got some speed up. This is the reason this value is greater than 1. And see, you have to find out the percentage of your throughput increase. Initially, you were having percentage as C. You were initially having 1. 1.33 is your new speed up, and previously it was 1, because if no changes has been done to the system, it will be 1. Then your speed up is 0.333 and it will be 33.3%. You have to find the percent value, then you have to multiply it with 100. Okay. Let us move towards next concept. It is 33.33. This is the answer. Okay, let us move towards next concept, which is, see, this question was asked in GATE CS 2015. We will read this question. Consider the following code sequence having 5 instructions. We are provided with the code sequence having 5 instructions, I1 to I5. Each of these instructions has the following format. This is the format which these instruction is going to follow. OP, RI, RJ, RK, where OP is the operation performed on the content of register RJ and RK. Whatever operation I have mentioned here, I am going to perform that operation on RJ and RK, and the result will be stored in this RI. That is, RI will hold RJ operation R. This is PRK. This is we are going to perform whenever this instruction is given to us. So these are the 5 instructions which we are going to have. First is add, multiply, sub, add, multiply. Now we are provided with the 3 statements. Let us see what are these statements. Consider the following 3 statements. S1, what S1 says, there is an anti-dependence between instructions I2 and I5. S2 says there is an anti-dependence between instruction I2 and I4. Third one is within an instruction pipeline, an anti-dependence always create one or more stalls. So these are the three statements. And now question, see what the question is asking. Which one of the above statement is correct? It is asking whether only S1 is true, only S2 is true. We have to check for the validity of these statements S1, S2 and S3. Let us see what this S1 is asking. There is an anti-dependence between instructions I2 and I5. First of all, what is anti-dependence? I have told you about anti-dependence when I discussed data hazards. We were having a hazard which is known as WAR, write after read hazard, which is known as anti-data dependency. When we are going to have this anti-data hazard, when an instruction is writing on register before this R can read the data. Suppose instruction I wants to read the data item R0 and this instruction J is writing that data item before reading of I. So this is the case of anti-dependence. And I told you for anti-dependence that register R, for one instruction it should belong to my input registers and for one instruction it should belong to my output registers. Let us check whether there exists an anti-data dependence between I2 and I5. See, I2 we are having registers as R1, R7, R1 and R3. And for I5 we are having R7, R8 and R9. There is no common register between input set of this and output set of this, as well as input set of this instruction and output set of this instruction. Then this condition is not satisfied. What we can say? See, so this condition is not satisfied. So what we can say, this R7 at this instruction I5 and I2 is not suffering with anti-data dependence, because for these instruction I2 and I5 to be suffering from anti-data dependence, this R7 should be here in place of R8 or R9, or this R7 should be here in place of R1 or R3. But this is not the case. So it is not suffering with anti-data dependence. Let us check for the instruction I2 and I4. So this statement is false. Let us check for I2 and I4. In I2, see, we are having input registers as R1 and R3. But in I4, this R3 is acting or present in the place of output register. So here anti-data dependence is existing. There may be chances if you are going to perform instruction scheduling for removing the stalls, this R3 is going to update this value before I2 can read it. So this is the problem. This is the anti-data dependence existing between I2 and I4. So this condition is true. Let us check for third statement. What is the third statement? Within an instruction pipeline, an anti-dependence always creates one or more cycle. What it is saying, that if your instructions are in such a way that anti-dependence exists between two instructions, then surely you are going to have some stalls. But see, this condition is false. We can remove this type of stalls by using register renaming. See how we are going to do it? See this thing, this R3 is to be read before this I4 can write on R3. I2 should read R3 before I4 can write R3 register. So what we can do, instead of using this R3, I will store this R3 in some random register RB, and we will give this RB to this instruction I2. Then this problem has been solved. So the problem of anti-dependence can be removed by using register renaming. Guys, this is the reason I have taken this question, because I want to tell you about this concept register renaming, which is used for removing the anti-data dependence stalls. So what we can say, anti-data dependence stalls can be removed by using register renaming. It is not always the case that you are going to have stalls if anti-data dependence exists between your instructions. So this condition or this statement is also false. So which of the option is correct over here? Option B, that is only S2 is true. Guys, this question is purely based on data hazards technique. And if you have not viewed or not studied that particular video, that particular concept, please refer that video again. There is no limit on referring a single video. You can refer the video many times you want. So just be clear with the concepts for solving the question. You can clearly see this question is so easy and it was asked for 2 marks. And your motive should get these type of marks. That is, you should not lose marks in such questions which are very easy directly based on the concept. So let us move towards next question. See, this question was again asked in GATE CS 2015 and it was again asked for 2 marks. Let us see what this question is asking to us. Consider the sequence of machine instructions given below. We are provided with a sequence of instructions. Here we are having 4 instructions. Let us see what is the next thing which is given to us in this question. In the above sequence, R0 to R8 are general purpose registers. These are the general purpose register present in CPU. In the instructions shown, the first register shows the result of operation performed on second and third register. See, this R5 is going to hold the result which is performed on this R0 and R1. And which operation which we are going to perform is mentioned with the help of opcode. This is the instruction decoding. This is the meaning of the instruction which is given to us. Let us see the next thing. This sequence of instruction is to be executed on a pipeline processor with the following 4 stages. That is, these instructions we are going to execute on a pipeline system with these 4 stages. Stages are instruction fetch and decode. This is mentioned as IF. Second is operand fetch. Third one is perform operation, and fourth one is write back of the result. In this pipeline, we are going to have 4 stages. Let us see the delay which each stage is going to take. See, it is given that IF, OF and WB stage is going to take 1 clock cycle for every instructions. See, this is going to take 1 clock cycle for processing the instruction. These two also going to take the 1 clock cycle for processing of the instruction. The PO cycle or the PO stage is going to take 1 clock cycle for addition or subtraction instruction. For addition or subtraction instruction, it is going to take 1 clock cycle. And for multiplication, it is going to take 3 clock cycle. And for division, it is going to take 5 clock cycle. So this is the data which is provided to us by this question. Let us see what this question is asking. The pipeline processor used operand forwarding from the PO stage to OF stage. It is given to us that we are going to use operand forwarding while solving these questions. Guys, one more suggestion. Till the time it is not mentioned in your question that you are going to use operand forwarding in your pipeline, do not apply the concept of operand forwarding while solving the questions. You may say that RISC pipeline is implementing this operand forwarding. So why we are not using it by default? Because this operand forwarding require extra hardware for its implementation. So you cannot directly use it. Till the time it is not mentioned in your question that operand forwarding is used, don't use it. Otherwise you are going to get the wrong answer. So let us see what this question is asking. The number of clock cycles taken for the execution of our instruction. Now we have to execute these 4 instructions and it is asking us the time or the clock cycle which is taken by these instructions. Let us execute. We are having 4 stages. You know how we are going to solve this question. We have done this so many times, guys. I want answer from you. I am just assuming that you are solving this question along with me. Now we are going to draw the time order execution sequence. Draw it with me. These are the clock cycles. Suppose it is clock cycle 1. In clock cycle 1, my first instruction, which is multiply RF, R0, R1, will be given to instruction fetching stage. Now it is in instruction fetching stage. In clock cycle 2, it will move towards OF stage, because this IF, instruction fetching and decode stage, is only taking 1 clock cycle. Then OF, in OF what we are going to do? Operand fetching, that is reading of R0 and R1 is done in this OF stage. Now I have read the value of R0 and R1. Next stage is PO, that is perform operation. And see over here, already I have written this thing that multiply is going to take 3 clock cycle in PO stage. So in CC3, CC4 and CC5, that is clock cycle 3, 4 and 5, my first instruction I1 is going to be in PO stage and operation is going to be performed over here. In CC6, it is moving towards WB, that is writing of the register is carried out in this stage. Okay. This is how your execution of instruction I1 will be completed. Let us see the execution of I2. This I2 will be inserted into my pipeline execution sequence at clock cycle 2. While my instruction I1 is in OF stage, because we are using the concept of pipelining, we can insert the new input before the completion of previous input. I will insert IF over here. When I1 is moving towards P0 stage, P0 stage or perform operation stage in clock cycle 3, we will move towards operand fetching stage. Now see, in this operand fetching stage, it requires to read values R2 and R3. We can directly read R2 and R3 because no operation has been performed on R2 and R3. We are going to read R2 and R3. Now, you will say this OF stage, operand fetching stage, is only taking 1 clock cycle, and in CC4 it can be inserted into perform operation stage. But it is not correct because your instruction I1 is taking 3 clock cycles in perform operation stage, and perform operation stage hardware is busy with instruction I1. So I2 cannot be inserted. So I2 has to wait in your OF stage till the time I1 completes its operation in PO stage. At CC5, I1 completes its operation, then it will be given to PO stage. See, this is the division operation, and division operation is going to take 5 clock cycles in the PO stage. Then in CC6 it will rest in PO. In CC7 again it is going to rest in PO. Now I will continue it over here. CC8, let us see. In CC8 again it is going to rest in PO, CC9, CC10 also. So now in CC11 it will move towards WB stage because your division or instruction requires 5 cycles to complete perform operation stage. So now we have completed instruction I2. Let us see execution of instruction I3. I3 will be inserted in clock cycle 3 while I2 was in OF stage. IF inserted. Now you will say that IF is going to take only 1 clock cycle, but you cannot insert this instruction I3 into OF stage in CC4 because your OF stage is busy with I2 instruction. So this I3 will remain in only IF stage. When I2 will move towards PO, it is going to be in OF stage. Now see, in this OF stage, it is going to fetch the operands, and the operands over here is R5 and R6. R6 is obtained by performing operation in instruction I2. That is, instruction I2 is updating the value of R6 and instruction I1 is updating the value of R5. And for performing these operations, you should read the updated value. This is the thing which we have studied while studying data dependencies. So see, here we can do one line. If you remember, pipeline processor uses operand forwarding from the PO stage to OF stage. See, this PO stage can do operand forwarding of R5 to OF stage for reading R5. R5 can be read over here, but R6 cannot be read till the time it completes operation in PO stage. So, till the time I2 is in PO stage, I will wait in OF stage. And the end of this PO stage, this will forward the operand to OF stage over here. And what I am going to do? I am going to do perform operation now. Here R6 is readed due to operand forwarding. In next clock cycle, what I am going to do? Perform operation and then write back. Okay. If we are going to execute the next instruction I4 will be inserted in clock cycle 6 and it will wait till the completion of OF stage in instruction I3. IF, IF, IF. Now when it moves towards PO, it will enter in OF stage. Now see, this OF wants to read R7 and R4. R4 can be read directly because no updation has been made to R4. But this R7 value is updated by instruction I3 and results are not stored yet. So what we are going to use? We are going to use operand forwarding. This PO stage is going to forward the result to OF. Then we are going to read R7. After reading this, we are going to perform operation and then write back. It is clock cycle 12 and it is clock cycle 30. So tell me the number of clock cycle required to execute these 4 instructions is? The number of clock cycle required is 13. So the answer here is 13. See, for solving this question, you need to draw the time order execution sequence and it is not that easy, but it is not that tough. If you are clear with your concept, draw it step by step. Don't be in hurry. Because guys, see, whenever you are in hurry, there are very less chances that you will get a correct answer. There are so much chances that you will get a wrong answer. So it is better to waste 10 to 20 seconds and get the correct answer instead of wasting your 2 to 3 minutes and get a wrong answer. I would suggest write each and every step very clearly. For such type of question, it is required to write each and every step. Suppose you are in hurry and you are not going to draw this time order execution sequence, then you will not know how to do this operand forwarding and you will definitely going to commit a mistake. So I would suggest for solving such type of question, never be in hurry, solve each and every step and then get the answer. Here your answer is 13. See guys, I have explained this thing. This is the reason this question might have taken 5 to 6 minutes, but when you are going to solve it on your end, you can solve it in hardly 2 minutes. So solve these type of questions properly. So guys, that's all about previous year questions on pipelining. Now from my side, I have tried to take those questions and try to cover each and every type of question. But see, now it is your time. I have completed the concept of pipelining. Now it is your time to act. Start solving the questions on pipelining. Take the previous year question from internet. You can download previous year question from net and solve. Take these CO question from that. Also take pipeline concept and solve the questions. Solve at least 10 to 15 years previous year question on pipeline. One more suggestion, since pipeline has been completed and while studying, you also get that this concept is not that easy. And for being fluent in this concept, you should remember each and every formula, each and every concept. So my suggestion is when you complete this particular subject, try to refer it after every 15 to 20 days. That is, revise the concept of pipelining after every 15 to 20 days. So that at the time when you are going to revise the whole syllabus, you need not to refer it again completely. You are going to save a lot of time at the time of revision. So my suggestion is refer this concept again and again because this is something you have not studied before. So that's all. So guys, I would suggest keep practicing. Practicing is the key for your success. More you practice, more you gain the confidence, more better will be your performance. So my suggestion is just practice. I have seen a lot of example. I am also the same example that practice is the main thing which is required for your success, or whatever you want to do, you need to be practice. For being perfect, you just need practice. First time you will commit some mistakes, second time reducing, and then one day will come, you will not commit a single mistake and you are fluent with your concept, fluent with everything. So guys, thank you for watching this video. In next video lectures, we are going to start with memory organization. Again, a very important topic in your computer organization subject. Till that time, keep practicing and stay updated and tuned for more videos. Thank you again.